You know, it's kind of amazing when you think about it. AI is making these incredible strides, but it's not just the software, right?
Not at all.
Yeah.
It's underpinned by some seriously advanced hardware, specialized chips.
Exactly. These chips are the real workhorses, and as AI gets more complex, they become even more critical.
It's a constant push and pull. The AI demands more, and the chip designers have to innovate. It's really fascinating.
Which leads us right into our deep dive today. Google's newest chip, the Ironwood TPU, their seventh generation custom AI accelerator.
Seventh gen already. Quite something.
And for our listeners, especially those tuned into the science corner aspect of tech, this is really a chance to look under the hood. We're exploring let's say, the physics and engineering behind this cutting edge stuff.
It's a great lens, definitely. Seeing how computational theory becomes, well, physical reality.
Something else that's interesting is how AI work is changing. It used to be all about training these huge models.
Right, the initial heavy lift.
But now there's this big shift towards inference, actually using the models. And Ironwood seems built for that.
That's the key point, I think. Previous TPUs were often, generalists for both training and inference. Ironwood is laser focused on inference.
Why that focus now?
Well, think about deploying AI widely. Serving predictions, answers to millions, maybe billions of people, that requires massive, efficient inference power.
Okay, so Ironwood is Google's bet on this age of inference. And I've read it's not just about speed, but also power efficiency, handling these complex thinking models.
Exactly. So our mission today really is to unpack what makes Ironwood tick. What are the key advancements, and why does it matter for where AI is going?
Couldn't have said it better. Understanding the hardware is, well, fundamental to grasping AI's potential and its limits.
Absolutely.
Okay, so let's dig into that shift to inference first. For our listeners who are maybe scientifically curious but not deep in AI jargon, could you break down training versus inference simply?
Sure. Think of training like a student cramming for a massive exam.
Okay.
You feed the AI model tons and tons of data, textbooks, examples, you name it. It learns patterns, relationships. It's very computationally intense, this learning phase.
Got it. Lots of studying.
Right. Then inference is like the student actually taking the exam,
Yeah.
using what they learned to answer new questions, solve problems they haven't seen before.
Applying the knowledge.
Precisely. That's inference, using the trained model on fresh data to make a prediction or generate some insight. Still needs power, but often optimized differently for speed and efficiency in getting the answer out.
That's a great analogy. So training does the heavy learning, inference puts it to work, and you're saying the demand for that putting it to work part is just exploding.
It really is. As AI moves out of the lab and into, well, everything, recommendations, translation, maybe future AI assistants, you need to serve those results efficiently to huge numbers of people, often in real time.
Right.
That takes colossal inference capability.
And that's where Ironwood comes in. Being designed specifically for inference, that's a big strategic set, isn't it?
It is. It signals that Google sees the main bottleneck shifting. It's not just training anymore. It's deploying effectively at scale. That's the inference challenge.
Right. Let's get into the Ironwood architecture itself then. What are the key sort of engineering breakthroughs? Performance and scale seem like the place to start. The numbers I saw were pretty wild.
They are quite something. Google's offering it in two main setups, one with 256 chips already powerful,
Okay.
and then a massive version scaling up to 9,216 chips in one pod.
9,000. Wow.
That scalability is really where it stands out.
And the total compute for that big one, 42.5 exaflops. How do we even, wrap our heads around a number like that?
It's hard, honestly. Google compares it to the current top supercomputer, El Capitan. That runs around 1.7 exaflops per pod.
Okay.
So Ironwood, in that large configuration, is offering more than 24 times the raw compute power.
24 times El Capitan. Good grief. That highlights the sheer parallel processing involved. For our Science Corner listeners, that's just immense. But why? Why need that much power just for inference?
It comes back to those thinking models Google talks about, things like Gemini 2.5. These aren't simple pattern recognizers anymore.
Right.
They're large language models. They use techniques like mixture of experts, MOEs, which are like teams of specialized AIs working together, advanced reasoning.
Okay.
So to give you a good, fast answer, especially when millions are asking questions at once, you need that kind of massively parallel computation.
Makes sense. Raw power is one thing, but efficiency is always crucial, especially in science and engineering. How's Ironwood on power consumption?
There's another major improvement area. They're
Sure.
saying it's twice as power efficient as the last gen, Trillium.
Which is already pretty new.
Exactly. And compared to their first cloud TPU back in 2018, it's nearly 30 times more efficient.
30 times in what, 7 years? That's
Yeah.
that's almost Moore's law territory for efficiency.
Yeah.
What does that mean practically?
Well, first, lower running costs,
That's
obviously.
right.
Power is a huge expense in data centers.
Sure.
Second, sometimes power availability itself is the limit. More efficient chips mean you can do more computing within the same power budget.
Right. Physical
And
constraints.
third, it's just, a more sustainable approach for AI overall. Less environmental impact.
That's definitely important. Okay, another term that popped up, high bandwidth memory, HBM. For the folks interested in the actual hardware, the nuts and bolts, what is HBM and why is it critical here?
Okay, so think of computer memory like a workbench, where you keep the stuff you're actively working on.
Right.
AI models, especially these huge ones, need to access and juggle massive amounts of data very, very quickly. HBM is a type of memory built for that much higher capacity and much faster data transfer speeds than, say, standard RAM.
And Ironwood features a big jump in HBM.
A huge jump. Each chip gets 192 gigabytes of HBM. That's 6 times more than Trillium had. And the bandwidth, how fast you can move data in and out, that's up dramatically too. 7.2 terabits per second per chip. 4.5 times Trillium.
Wow. So massive capacity, massive speed. How does that help the AI actually run better? What does the user maybe indirectly experience?
It means the chip can keep much more of the AI model and the data it needs right there on the workbench, basically.
Less fetching from slower storage.
Exactly. Constantly going off chip to get data is slow, a major bottleneck. With more, faster HBM, the calculations can happen much quicker because the data is right there. Big performance boost, especially for memory-hungry tasks.
Okay, that makes sense. Then there's the inter-chip interconnect, ICI. What's its job, especially when you have thousands of these chips working together?
Right, in these huge systems, the chips aren't working in isolation. They have to talk to each other constantly, share data, coordinate tasks.
Like a network between the chips.
Pretty much, a very high-speed internal network. The ICI is crucial for anything involving distributed computing, where the problem is broken up across many chips.
And Ironwood improves this interconnect too.
It does. The ICI bandwidth is up to 1.2 terabits per second bidirectional. That's about 1.5 times faster than Trillium.
So faster chatting between the chips.
Which means less waiting, better coordination, and you get more benefit from having all those chips working in parallel. Vital for large-scale inference.
Got it. Now, SparseCore. That sounds specific. An accelerator for ultra-large embeddings. For our scientifically minded listeners, what are embeddings here and why need a special accelerator?
Okay, embeddings. In a lot of AI, especially language or recommendations, you represent concepts, words, items, users as points in a high-dimensional mathematical space. These points are vectors called embeddings.
Okay.
Their position encodes meaning. So words with similar meanings might have embeddings that are close together in that space. Ultra-large just means these embeddings can have like millions or billions of dimensions for really complex models.
Billions, wow.
Yeah. And often, these embedding vectors are sparse, meaning mostly zeros. Calculating with these huge sparse vectors is tricky for standard processors. SparseCore is custom hardware built to do those specific calculations very quickly.
So it's specialized for that kind of math, and Ironwood expands what SparseCore can do.
Seems so. They're suggesting the enhanced version can accelerate a wider range of tasks, maybe even moving beyond just AI into things like finance or scientific simulations where you find similar large, sparse data structures.
Interesting potential there. Lastly, on hardware liquid cooling. Sounds pretty high-tech. Why is that needed? Thinking about the physical engineering side.
Well, when you pack so much computing power into a chip like Ironwood, it generates a lot of heat, especially under constant heavy AI workloads.
Like running flat out all the time.
Exactly. Normal air cooling just might not be enough to keep temperatures down. And if it gets too hot, the chip has to slow itself down. That's called throttling or could even be damaged.
So liquid cooling is just much better at removing heat.
Much more efficient. It lets the chips run at their peak performance consistently without hitting those thermal walls, essential for reliability in these demanding systems.
Okay, so it's really about enabling sustained peak performance. Now, hardware is only half the story, right? Software is crucial. What's happening on that front for Ironwood?
Absolutely critical. Google has this runtime called Pathways, developed by DeepMind. It's designed specifically to manage distributing the work across all those TPU cores across many chips. efficiently.
So Pathways is the conductor for this massive orchestra of chips.
That's a good way to put it. And it lets you harness the power of these huge Ironwood pods effectively.
And Google Cloud customers can use Pathways with Ironwood.
Yes, making Pathways available on Google Cloud is key. It means users aren't limited to just one pod. They can potentially scale workloads across hundreds of thousands of Ironwood chips if needed.
Hundreds of thousands. The scale is just mind-boggling.
It really opens the door for tackling incredibly ambitious AI problems.
What about fitting into existing developer workflows, like the common frameworks, PyTorch, JAX?
Google knows that's vital. Ironwood is accessible through optimized versions of those popular frameworks.
Good. So developers don't have to completely relearn everything.
Right. It lowers the barrier to entry for using this new hardware, which is smart.
So they're providing the engine and making it easier to drive. Stepping back then, this age of inference idea Google keeps mentioning, what's the bigger picture they're painting, and how is Ironwood enabling it?
The vision seems to be AI becoming more proactive. Less just answering direct questions and more about anticipating needs, actively finding and synthesizing information, being more of a collaborator.
AI as an active assistant, not just a passive tool.
Something like that, a shift towards more autonomous, intelligent agents.
That sounds like a pretty profound change in interaction, and Ironwood is the foundation for that.
It's a key enabler. To have AI agents capable of that kind of reasoning and proactivity, especially deployed widely, you need enormous, efficient inference power. Ironwood is built to provide exactly that computational backbone.
And just to clarify for listeners, this isn't something you'll buy at a store, right?
No, no. While the science is cool for everyone, Ironwood is being offered through Google Cloud. Customers access it via those 256 chip or 9,216 chip pods as part of Google's cloud infrastructure. It's enterprise scale stuff.
Okay, makes sense given the power and complexity. So as we wrap up this deep dive, what are the main things our Science Corner listeners should take away about Ironwood?
I'd say the key thing is that Ironwood is a really significant step in specialized AI hardware. It's heavily optimized for inference, tackling that growing need.
Right.
And it does this with big improvements in performance, power efficiency, memory capacity, and speed, and how the chips connect, all geared towards running these next-gen thinking models.
And for our listeners, it's just a fantastic example of engineering pushing the limits, right? Directly impacting where AI can go.
Exactly. Building something like Ironwood involves solving incredibly complex problems in parallel computing, memory, power, cooling, all at a massive scale. It shows that relentless innovation cycle in hardware driven by AI's needs.
So looking ahead, it's exciting to think what this kind of hardware unlocks. What's a final provocative thought for our listeners to chew on?
Maybe think about this. How will these powerful, efficient inference chips like Ironwood change access to advanced AI? As it gets potentially cheaper and easier to run sophisticated models, what new applications might pop up that we can't even imagine yet?
Democratization through hardware.
Perhaps.
Yeah.
And also, are there fundamental limits? Physical limits, maybe theoretical ones, that these specialized chips will eventually run up against as we keep pushing AI harder and harder.
Deep questions indeed. Well, if you want to explore more, definitely look up AI accelerators, distributed computing, AI infrastructure. There's a lot out there. Thanks for joining us on this deep dive into the science behind Google's Ironwood TPU.